On Tuesday, I thought I did such an incredibly poor job on the conditional probability problem at the end of the chapter 3. I thought I'm going to try to redeem myself and do that example again. And then I'm also going to do an example from your homework. I've had a couple of questions on this example, and I thought it'd be a good idea to look at it, because the problem with the conditional probability problems is that it can be unclear what they're telling you and unclear what they're asking you. So you have to be really careful in reading the problem. Okay, so I'm going to share my iPad, which I found when I'm at home does a much better job. There we go. If I can get the iPad to pop up. All right. Okay, so this is the problem we were looking at on Tuesday about the cancer and the cancer test. And I did a really poor job on this, so I thought I'd give it another try. And this is the end of section 3.5 in Bayes' theorem. So the problem states that the probability of having a type of cancer in a population is 3%. So I'm going to go ahead and write that down. So they tell me the probability of having this type of cancer is 3%. Now, conversely, and I might not know this until I start writing down Bayes' theorem, but conversely, I'm going to need the probability of not having cancer. So I'm going to write that down. If 3% of the population has this type of cancer, then 97% of us don't. So I'm going to write that as no cancer. And again, I might not know that I need this until I start writing out Bayes' theorem, but since I know I'm going to need it, I'm going to go ahead and write it out. And then what else do we see? A test. Get my internet connection back up. A test for the disease is 99% accurate if the person has the disease. So what this means is that it's 99% accurate finding the cancer if you've got it. So what this is a conditional probability. The probability that you test positive given you have cancer is 99%. And that's a good thing, right? It's good that it's actually detecting the cancer that I have. But this is a conditional probability. So the probability that it detects my cancer so that it tests yes or positive, given that I have the cancer, is 99%. So if it's 99% accurate, so it finds the cancer 99% of the time, 1% of the time it won't. What do we got here? For some reason, I'm not being able to see the chat. See if I can reduce this, do a little playing with my screen. Here we go. There we go. Now maybe I can see the chat. I'm mumbling to myself, which is going to sound great on the Zoom call, isn't it? All right. So in other words, I have another conditional probability. The probability that it doesn't detect or it tests negative, given I have cancer, is 1% of the time. So 1% of the time, it doesn't catch the cancer. Okay, now what else does it tell me? It says 98% accurate if the person does not have the disease. So in other words, if I don't have cancer, 98% of the time, it tells me I don't. Okay, so this is another conditional probability. And this is a conditional probability that says I'm going to test no given I don't have cancer. And that is accurate 98% of the time. So 98% of the time, if I don't have cancer, it's telling me I don't. So it's no. So 2% of the time, you're going to get this false negative. So false negative means yes. It tests yes that you have the cancer when you actually don't. So this would be yes, given that you don't have cancer. That would be 0.02. So at this point, I got so much going on here that I'm thinking a tree diagram might be the way to go, because I've got 6 probabilities already listed, and I haven't even decided what they're asking me for yet. So what are they asking me for? What is the probability of a person having the disease if the test result is positive? Okay, so what they're asking me for is what's the probability that I have cancer given that it tested yes. So they're asking me the opposite of the conditional that they gave me, that given I have cancer, that I test yes given I have cancer. What they're asking me for is what's the probability of me having cancer given that I tested yes. So what they're asking me for is this. And I'm going to have to use some Bayes' theorem to figure this out. And again, at this point, I've got so many probabilities. And when I start writing Bayes' theorem, I'm thinking, I might need a tree diagram for this. This is complicated. There's lots of branches going on here. Well, there's not that many branches, but it's kind of complicated. So to try to figure this out, I might want the tree diagram, right? So what I'm looking for is the probability that I have cancer given that I've tested yes. So here's what they did, and here's all the probabilities that I listed. And for some reason, I'm not getting my equals showing up here on my PowerPoint. Yeah, we'll put those in. So here's all the probabilities that they gave me. And we have that there's a 3% probability that I have this type of cancer. If you just randomly pick somebody from the population, there's a 3% chance that they have this cancer. So that's that first branch. The second branch is there's a 97% probability that you don't. If I randomly select somebody from the population, there's a 97% probability that they don't have the cancer. So those are those first 2 branches, and those are those 2 probabilities right there. Now, if I have cancer, there's a 99% accuracy for the test for this cancer. So if I actually have the cancer, this test is going to find it 99% of the time. So it's going to test yes when I have the cancer. That's this branch right here. It's going to test no 1% of the time when I actually have the cancer. So that second branch is that I have cancer, but it tested no. So it's no given that I have cancer. Okay. Now, 97% of the population that doesn't have cancer, the no cancer branch, of those, 2% are going to test positive. So it's a false positive. But 98% of those, when they conduct this test, it's going to test accurately that they don't have the cancer, and they really don't. So the 0.98 is the probability that I test no, given that I don't have cancer, 98% accurate. The other branch, the 0.02 branch, is that it gives me a false positive. It tells me, yes, I do have the cancer when I actually don't. So 2% of the time, it'll scare the daylights out of you because it'll tell you have cancer when you actually don't. So you have to get more testing. Now let's talk Bayes' theorem. Okay, so the formula for Bayes' theorem is the probability of B given A is the probability of B times the probability of A. We don't have any equals in here. For some reason, my equals are not showing up. It's the probability of B times the probability of A given B divided by the probability of A. So what we're looking for, the probability that we have cancer given we tested yes, we got a positive test, then would be the probability that I have cancer using Bayes' theorem above it times the probability that I have cancer given that I tested yes, divided by the probability of a yes. And I don't know what that is. I don't know what the probability of the yes is. That's an unknown for me. Now, I do know what the probability of having this type of cancer is. That's the 0.03. And I do know what's the probability of testing yes if I actually have the cancer. The test is 99% accurate. So I do know what the numerator of this is, but I don't know what the denominator is. And that's where this, this tree chart is invaluable, because where do we have two yeses? Well, we have two yeses right here. And since these are mutually exclusive events, we can actually find those probabilities by just finding the two probabilities and adding them together. That's supposed to be a plus sign right there. So I have two branches where I have the probability that I get a yes. And that's the probability of a yes given I have cancer times the probability that I have cancer. That's the first branch up there, the first yes. And the second yes is that I don't have cancer and that I tested yes that I did. So that's that second branch down there. So the two probabilities for the yeses, I'm going to add those together. I have 0.03 times 0.99, and I have 0.02 times the 0.97, and I add those two together. And that gives me the probability of the two yeses. And so then I can figure out what the probability is of that. I got a yes given, or I have cancer given that I got a yes, and that's 0.6049. So that's actually kind of reassuring that it's only 60% of the time that you actually have the cancer if you tested yes. That means 40% of the time you don't. So that's kind of a nice thing, kind of a nice probability to find. All right, so hopefully I redeemed myself ever so slightly with that horrible job I did on Tuesday explaining that example. But again, when I was doing this, just by looking at it, when you get down here to this probability of a yes, and all you have is conditional probabilities, that gets really difficult to find using the conditional and using Bayes' theorem. So this is just begs for me to create a tree diagram just listing all these probabilities. We had so much going on that a picture just helped immensely. Now the next example of a conditional probability, a picture just really didn't help me so much because there's just not that much going on, not near as much as what's going on in this example. And this comes from your homework. And I think it's the last problem in that last section. Why won't PowerPoint cooperate? You know, if it doesn't cooperate one way, we'll make it cooperate another way. So this is the example that you have where you're talking about voter approval. So a survey reported, and you'll have exactly the same problem, the numbers are just different. A survey reported that 77% of registered voters in California approved of allowing two people of the same gender to marry and have regular marriage laws apply to them. So the first sentence tells you that the probability of California voters approving of this measure is 77%. So the probability that a particular voter, if I just go to California and I have the whole population of all the voters, and I randomly pick one of them out of all the voters in California, randomly pick a voter, then 77% of the time I'll get somebody that approves of this. So that's 0.77. Okay, let's read the second sentence. Among 18 to 39-year-olds registered voters in California, 86 approved of gay marriage. So now you've got a conditional because their approval depends on what age they are. So what you have is among those 18 to 39-year-old voters, so if I go to California, now I'm picking from the pool of just the 18 to 39-year-olds. That's my pool. And if I randomly pick one of those people, then 86% of the time I'm going to pick somebody who approves of this proposal. So what I have here is a conditional probability. My pool of voters now is just the 18 to 39-year-olds. And of those, 86% approve. So that's a conditional probability that given they approve given they're between that age. Because it's a conditional probability because now I've decreased the pool of voters and I'm just looking at those 18 to 39-year-olds. And that is going to be what, 86%? All right, 40% of California registered voters are between the ages of 18 and 39. So now they tell you how many of those voters. So the entire population of California voters, those who are registered to vote, 40% of those fit that age category. So that's the probability if I randomly go to California and I pick one person out of the population of all registered voters, 40% of the time I'll pick somebody who's between 18 and 39. So the probability that someone's between 18 and 39 is 40%. Okay, now what's the last question? Out of the voters who approved of gay marriage. So now you've narrowed your pool, the people you're looking at, only to the people who approved of it. So that's who you're looking at now. And out of those, how many of them are between 18 and 39? So now you're looking at what's the probability that they're that age given they're in this pool of people who approved of it. So what you're looking for is what's the probability they're 18 to 39 given they approved of it. Okay, and now we can use Bayes' theorem to figure that out. We have everything we need to know to be able to figure that out. So Bayes' theorem says that the probability that I'm between 18 and 39, given I approved of this thing, this proposal, is by definition the probability that I'm both 18 to 39 and I approved. And this is the formula by definition. This is not something I'm thinking of. This is the formula, Bayes formula. And I approved divided by the probability that I approved. That's what the formula says. Now, what I don't know is the and. I don't know the numerator. I know the percentage that approved. I know that. But I don't know what that P of 18 to 39 and A is. I don't know what probability that is, what percentage did that. So I need to find it. So I'm going to use Bayes' theorem again to find that and. So Bayes' theorem says that the probability that I'm between 18 and 39 and I approved, I'm going to use an ampersand, and I approved, is, using Bayes' theorem, the probability that I approved given I'm in that age group times the probability that I'm in that age group, and I ran out of room. So this formula that I just wrote down is Bayes' theorem, just written a different way. So the probability that I'm this and this is the conditional probability that I approved given I'm in that age group times the probability I'm in that age group. That's Bayes' theorem. So this is going to be, and I know those two things, that's 0.86 times what's the probability that a voter's in that age group? 0.4. So if I take 0.86 and multiply it by 0.4, I get the probability that a voter in California is between 18 and 39 and they approved of this measure. So that's going to be, my calculator says 0.344. So now I know everything in this formula up here. So the probability that I'm between the ages of 18 and 39, given that I approved, is this probability of 0.344 divided by the probability that I approved, 0.77. And I take my handy dandy calculator out and I get 0.44673. And I carried it out to so many decimal places because my OpenMath is going to say, okay, now round this off as a percentage to 4 decimal places. So they want me to write this as a percentage, which would be 44.6753%. So now if I go to California and I only look at the people who voted to approve this measure, just them, that's the only pool I'm looking at. Of those, how many of those people who approved are between 18 and 39? That would be 44.6753%. So 45% of them are between that age group, which means 55% aren't in that age group. Okay, and that's the end of chapter 3. Fun, fun, fun. So in my previous class, I don't know that all of you have taken college algebra. I think that is not the case, that all of you have not taken college algebra. College algebra, you spend a lot of time talking about functions. 3 chapters. So I told them this morning that you can't have function without fun. They were not amused. All right. We're going to start our discussion of random variables and probability distributions. So in chapter 4, and chapter 5, and chapter 6, and I don't remember how far it goes, up to like chapter 12, we talk about probability distributions. And in this chapter, we're going to look at discrete probability distributions. So do you remember from chapter 1 what it means for something to be discrete? Remember, we looked at different types of data. And if it was discrete data, it's data that you count. So we're going to be looking at information that you can actually sit there and count. Then we'll move on to continuous probability distributions, which means now we're going to look at data that's continuous that you can't count. So we're going to use different probability distributions for that kind of data. But right now we're going to use it, just look at discrete data. So the first thing we're going to do in the first 2 sections, 4.1 and 4.2, is we're going to talk about what a probability distribution is. Probability distribution function. See, you can't have function without fun. Then we'll calculate expected values. And you can calculate these by hand if you don't have a lot of data, but your calculator can calculate the expected value just by using the relative frequencies. Remember way back when we talked about, and I think even in chapter 3, we talked about that if you look at the relative frequency of your data, that is the probability of you getting that value. So probability and relative frequency are the same thing. So you can actually put in your calculator a table in your list 1 and list 2 of your data values and then the relative frequency of those data values, and then calculate your statistics on that. So you can do this using your calculator. Then we're going to get into our 4 examples of discrete probability distribution. We're going to talk about the binomial, the Poisson, the geometric, and the hypergeometric. So we're going to look at those 4 specific types of discrete probability distributions. And each one of them has their unique application. And it's pretty straightforward which one you use for what. Okay, some examples of random variables and discrete probability distributions. So you're a student and you're taking a 10-question true-false test, but you didn't study, so you're just going to guess. So each of these 10 questions, you're going to purely guess true-false. So what's the probability that you get a 70%? So this is a discrete probability distribution, okay? Small phone companies might be interested in the number of you can count the number of long distance phone calls their employees make during the peak time of the day. Suppose the average is 20 calls. This is Poisson, by the way, in case you're interested. What is the probability that the employees make more than 20 long distance phone calls during the peak time? So this is a discrete probability distribution. It's Poisson. We'll talk about that later. But it's because you can count the number of calls that they make. So these 2 examples illustrate 2 different types of probability problems involving discrete random variables. What's a discrete random variable? We'll talk about that in just a second. Recall that discrete data are data that you can count. A random variable describes the outcomes of a statistical experiment in words. That's what a random variable is. It's a description of your outcomes. The values of a random variable can vary with each repetition of an experiment. So for the small companies in the long distance calls, what's the probability they make more than 20? So the random variable is the outcomes of the experiments, that they make long distance calls during their peak time. And what values could that random variable take on? I don't know, they could make no calls, 1 call, 2 calls, 5 calls, I don't know. So that's the value that your random variable can take on. Okay? So when we talk about random variables, we use capital variables, typically capital X and capital Y. So when you see a capital X or Y, that's a description of the outcomes of your experiment. Lowercase letters like X and Y, they actually are the values that your random variable can take on. So they're actually numbers. So the big X, big Y are descriptions in English. The little x and the little y are actually numbers that the random variable can take on. So if capital X is a random variable, then X is written in words, capital X is written in words, and little x is given a number. For example, so you run an experiment where you're flipping a coin. So X, capital X, could be, the random variable could be the number of heads you toss when you toss 3 coins, the number of heads you get when you toss 3 coins. So I have 3 coins, I toss them. What's the number of heads I get? That's my random variable. Now, what values can that take on? Well, if you look at the sample space for tossing 3 coins, what could happen? Well, if you toss 3 coins, you could get 3 tails, so no heads. If you toss 3 coins, you could get 2 heads. So you could get either tail, head, or the first coin could be a head, the second coin could be a tail, the third coin could be a head, or the first 2 coins could both be heads and the third one a tail. So you got 3 different outcomes where you get 2 heads. Then you could get just 1 head, so you could toss your 3 coins and the first one's a head and the second 2 are tails, or the first is tail, the second is head, the third is tail, or the first 2 are tails and the last one's head. And the last outcome you could get in your sample spaces, they could all turn out to be heads. So if my random variable is the number of heads when you toss 3 coins, what are the number of heads we get when we toss 3 coins? Well, we could get none. That's this outcome right here. So that's 0 heads. So x, little x, could take on the value of 0. It could also take on the value of 1. So we have 3 outcomes here where I only get 1 head. So the random variable could take on the value of 1, and that's little x. So little x could be 0, no heads, or 1, 1 head. It could also be 2, because you have 3 outcomes where you got 2 heads. So your random variable could take on the value of 2. And then last but not least, it could take on the value of 3, because you could theoretically toss 3 coins and get all 3 heads. So the last value that your random variable could take on is the number 3. So big X is the description, the number of heads you get when you toss 3 coins, and little x takes on the values of 0, 1, 2, and 3. And from this, you can find the probabilities, which is what we did in chapter 3, of each of these outcomes. What's the probability that you get no heads? Well, no heads, there's 1 out of 1, 2, 3, 4, 5, 6, 7, 8 different possibilities. So 1 out of 8. So you can calculate what these are. Okay, so specifically in section 4.1, we're going to talk about discrete probability distributions. And there are 2 characteristics of a discrete probability distribution. The first characteristic is that each probability has to be between 0 and 1 inclusive. So you can't have probabilities bigger than 1, and that makes sense anyway. But the sum of all the probabilities have to equal 1. So when you add them all up, you have to equal 1. So let me show you what I mean. Okay, so this is an example of an experiment. So a child psychologist is interested in the number of times a newborn's crying wakes its mother after midnight. So for a random sample of 50 mothers, the following information was obtained. So our random variable capital X is a description of what we're looking at. It's the number of times per week a newborn baby's crying wakes its mother after midnight. That's what they're interested in looking at. When they sampled these 50 mothers, the mothers told them how many times in the week the baby's crying woke them up after midnight. And what values can our discrete random variable take on? Well, 0. So at least one mother, well, in this case, it was 2. We'll talk about that in a second. So a mother told them that the baby never woke them up in the whole week. And a mother said once, another mother said twice. So the random variable can take on the values from 0 to 5 times. The baby never woke the mother up to the baby woke the mother up 5 times during the week after midnight. So over here, we've created a table. So our psychologist looks at the random variable and the different values that the random variable can take on. And that's this over here. So no mother told the child psychologist that the baby woke them more than 5 times. 5 was the maximum number of times during the week. Lucky mom. Anywho, now the second column is the probabilities that we get this value for our random variable. So what we see here is the probability that the random variable takes on the value of 0, or that the baby didn't wake the mom up. Well, 2 mothers out of the 50 said that the baby never woke me up after midnight during the week. So the probability that X takes on the value of 0 is 2 out of 50. That's its relative frequency. 2 out of the 50 said that the baby didn't wake them up. So this is the relative frequency. And 11 moms out of the 50 said the baby woke them up once. So the probability that the random variable takes on the value of 1 is the relative frequency, or 11 out of 50. 23 of the moms said that the baby woke them up twice in the week. So the probability that the random variable takes on the value of 2 is 23 out of 50, the relative frequency. 9 of the moms out of 50 told their child psychologist that the baby woke them up 3 times. So the probability that the random variable takes on the value of 3 is the relative frequency, 9 out of 50. Probability that the random variable takes on the value of 4 is 4 out of 50. And the probability that the random variable takes on the value of 5 is 1 out of 50. Only one of the moms out of the 50 said that the baby woke her up 5 times during the week. Now, for this to be a discrete probability distribution, what has to be true is that each of these probabilities must be between 0 and 1. You can't have a probability less than 0 and 1 greater than 1. So we have, again, all these probabilities, all these relative frequencies are less than 1. 2 out of 50 is less than 1. 11 out of 50 is less than 1, etc. And the sum of these probabilities has to equal 1. So you can't leave anybody out of your survey. Each one of these has to be counted. So if I add those 6 probabilities together, I will get the value of 1. So those are the 2 criteria that must be met for this to be a discrete probability distribution. Each probability must be between 0 and 1 inclusive. So you could have a probability of 0. As a matter of fact, if we listed 6, the probability of anyone saying 6 was 0. Nobody said 6. So the probability has to be between 0 and 1 inclusive, and the total probabilities have to add up to 1. Okay, so let's look at this one. A hospital researcher is interested in the number of times the average post-op patient will, those of you who are going to be nurses, you might be interested in this. How many times the average post-op patient will ring the nurse during a 12-hour shift? This might be important information for you to know so that you can staff properly, right? This is something a nursing supervisor might be interested in. For a random sample of 50 patients, the following information was obtained. So our random variable is going to be the description of this experiment. What are you interested in? You're interested in the number of times the patient rings the nurse in a 12-hour shift. So that's our random variable, capital X. Now, what values can this random variable take on? Well, it depends on the outcomes of your experiment. So when you surveyed these 50 patients, you found that some patients didn't ring the nurse at all in the 12-hour shift. And the maximum number of times that a patient rang the nurse during a 12-hour shift of this survey of 50 was 5 times, okay? So what's the probability that the random variable takes on any of these 6 values? Well, it depends on how many patients did this. It's the relative frequency of this. So the first column in our table are the values that our random variable can take on. So our random variable can take on the values from 0 to 5. Then what's the probability that we get X of 0? Well, we had 4 patients out of the 50 that didn't ring the nurse in the 12-hour shift. So the probability that the random variable takes on the value of 0 is the relative frequency of that, or 4 out of 50. What's the probability that the random variable takes on the value of 1? What's the probability that a patient only rang for the nurse once during a 12-hour shift? Well, the relative frequency of that was there were 8 patients who only rang the nurse once. So it's 8 out of 50. What's the probability that the random variable takes on 2? Well, again, out of these 50 patients, there were 16 of them that rang for the nurse twice. What's the probability that they rang the nurse 3 times, that the random variable takes on the value of 3? Well, there were 14 out of the 50 patients that rang the nurse 3 times, 6 out of 50 rang the nurse 4 times, and 2 out of 50 rang the nurse 5 times. So the first column is the values that our random variable can take on. In the second column is the probability that our random variable took on that value. So it's the relative frequency of that. Now, for this to be a discrete probability distribution, each of those probabilities must be between 0 and 1 inclusive, which they are. And when I add them up, I better get 50. So if I add 4 and 8, 12 and 16, what's that, 28 and 42, 42 and 8 is 50. So 50 over 50 is 1. They're pretty straightforward, discrete probability distributions. Okay, so suppose Nancy has classes 3 days a week. Pretty typical for a lot of you. She attends classes 3 days a week, 80% of the time. Tisk, tisk, Nancy. Tisk, tisk. You should be attending way more than 80% of the time. 2 days, 15% of the time. Tisk, tisk, Nancy. 1 day, 4% of the time, and no days, 1% of the time. Suppose 1 week is randomly selected. Create a discrete probability distribution. So we need to, first of all, define what our random variable is going to be. And then we're going to create a table to describe this probability distribution. Okay, so we're going to let capital X be our random variable. And what are we interested in? We're interested in the number of days that she attends class during this randomly selected week. So what we're interested in is the number of days Nancy attends class per week. So we're going to set up our table. And we're going to look at what values this random variable can take on. So she's got 3 classes. 3 days a week that she attends class. 3 days a week she attends class. So she can attend class no days, 1 day, 2 days, or 3 days. So those are the values that my random variable can take on. Now we're going to look at the probability that my random variable takes on that particular value. So what's the probability that my random variable takes on the value of 0? Well, what does she say? 1% of the time she doesn't attend class during the week. So that would be 1%. Or usually we write probabilities as decimals and not percentages. So the probability that she doesn't attend class at all during the week is 0.01. What was 1 day a week? 4%? So the probability that my random variable takes on the value of 1 is 4%. 2 days a week, was that 15% of the time? And 3 days that she attends all 3 days is 0.8, 80% of the time. All right, for this to be a discrete a discrete probability distribution, I will spit it out. Each of these probabilities must be between 0 and 1, which they are, and they have to add up to 100%. They have to add up to 1. So if I add those all up, 0.1, 0.04 is 0.05, plus 0.15 is 0.2, 0.2 plus 0.8 is 1. So this is a discrete probability distribution. But tisk on Nancy, should be attending class every day of the week, 100% of the time. I'm the teacher, I can say that. All right. And that's a discrete probability distribution. Okay, so the next thing we're going to look at is how to find this thing called expected value and how to find the standard deviation. So given a discrete probability distribution, can you find this thing called expected value? Can you find the standard deviation? And the answer is yes. Because if you look at the one we just looked at, again, what is that second column? That second column is the relative frequency. So you could actually pop this into your calculator, put the values that your random variable can take on in your first list. So you can put this in L1. And you can put the frequencies in L2 and calculate the one variable statistics. So you can certainly do this on your calculator, but let's show you what it means to do it by hand. But you can do this on your calculator. Let's define what we mean by expected value. The expected value is often referred to as the long-term average or mean. So expected value is the mean of your probability distribution. That's what it is. This means over the long term, doing an experiment over and over and over and over, you would expect to get this average. So for example, if you toss a coin and record the result, what's the probability that the result is heads? If you flip the coin 2 times, does the probability tell you that the flip will result in 1 head and 1 tail? And the answer is maybe not. But if you toss a fair coin 10 times and record 9 heads, that probability does not describe the short-term results of an experiment. It gives information about what can be expected in the long term. So again, if I flip a coin twice, do I get exactly 1 head and 1 tail? Probably not. Using the word probability, probably not. But over the long term, if I toss the coin over and over and over and over and over and over again, I would expect half the time to get heads and half the time to get tails if it's a fair coin. So Carl Pearson once tossed a fair coin 24,000 times. How long did that take him to do? A long time. And he recorded the result of each toss, obtaining 12,012 heads in the 24,000 tosses. And that's about half, which is what you would expect. So this introduces the concept of the law of large numbers. And the law of large numbers says that as the number of trials in the probability experiment increases, the difference between the theoretical probability of an event and the relative frequency, which is the experimental probability of the event, approaches 0. So the more times you do an experiment, the closer the theoretical probability and the relative frequency get. So the theoretical probability, I mean, if you flip a coin, you would expect the probability of getting a head to be 1/2, 1 out of 2. Well, that may not be true if you toss the coin 10 times. It may not be a half. But the more often you do this, the number of times you increase the experimental trials, then the closer the experimental probability, the relative frequency, will get to 1/2. So when evaluating the long-term results of a statistical experiment, we often want to know what the average outcome is. So the long-term average is known as the mean or expected value of the experiment, and we use the Greek letter mu to denote this. In other words, after conducting many trials of an experiment, you would expect this average value. Oh man, I lost everything in this one. It's because I have, I'm using PowerPoint and I didn't fix the, oops. I don't know if it'll let me pick my eraser out here. If there's a will, there's a way. So this is the sum. Okay, so what this means is, and it's correct in the slides in Blackboard, it's just incorrect because I'm using my iPad this morning instead of my Surface Pro, and the equations are not quite up to date. So what this means is, to find the expected value, you find the values that your random variable can take on, that's little x, and you multiply that by the probability. And then you add all those together. So you take the value of the random variable times the probability that the random variable takes on that value, multiply those together, and then add them all up. Or you can put it in your calculator, whatever works for you. The standard deviation is way more difficult to calculate for a probability distribution, so you probably are going to want to put it in your calculator to do that. So to find the standard deviation, you take this mean that you calculated on the previous slide, whatever that is, and you subtract it from each value of your random variable. So whatever values your random variable can take on, you subtract the mean from each one of those, you square it, and multiply that by the probability that it can take on that value of the random variable, and then take the square root. Way too cumbersome to do. So again, you can pop this in your calculator and do it that way. So let's do an example. A men's soccer team plays soccer 0, 1, or 2 days a week. The probability that they play 0 days is 0.2. So 20% of the time they don't play at all during the week. The probability that they play 1 day is 0.5. So 50% of the time they play 1 day. The probability that they play 2 days is 0.3. So 30% of the time they play 2 days a week. Find the long-term average or expected value mu of the number of days per week the men's soccer team plays soccer. So to find the expected value or the long-term average mu, we simply multiply the value of the random variable by its probability and add that up. So the probability, we have 0, 1, and 2 days. The probability they don't play soccer at all during the week is 0.2. The probability that they play 1 day a week is 0.5. The probability that they play 2 days is 0.3. Again, so for this to be a discrete probability distribution, each of those probabilities must be below 1, above 0, and below 1, between 0 and 1, inclusive. And you have to add them up and get 1, which is the case. So to find the expected value, mu, we take the value that the random variable can take on, and we multiply it by the probability. And then we add those all up. Okay, so we take 0 times 0.2, we add 1 times 0.5, we add 2 times 0.3. So we get 1.1. Now, what's this mean? How do we interpret this? This means over the long haul, so for weeks and weeks and weeks and weeks, on average, they play 1.1 games a week. Now, you know that you can't play 1.1 games a week. Maybe you can if you get rained out. I don't know. But you don't really play part of a game. So in any given week, you're going to play a discrete number of games. You can count. But on average, over the long term, so if we look at a whole year, 52 weeks, on average, they play 1.1 games a week. Some weeks they play less than 1 game a week. Some weeks they play more. So on average, they play 1.1 games a week. All right. Now, to find the standard deviation, this is where you say, okay, I'm done with this. I'm going to take my calculator out and do this. Because in your calculator, you'd put, in L1, you'd put the value of your discrete random variable. So you'd put the 0, 1, 2, and 3. And in L2, you would put the relative frequencies. You would put the probability. So you'd put the 0.2, the 0.5, and the 0.3. And then once you have those in your lists, you're going to go over to your stat menu. And if we have time, we might do this. We might have time. You'd go to your stat menu and you'd go edit. You'd put this information in your lists. And then you're going to go back to your stat menu. and you go over to calculate, and you calculate your one variable statistics. And your values are going to be in your first list, and then the frequency would be in your second list. So you put your values in L1 and your frequency would be L2. Okay, if time permitting, we'll do this. So to do standard deviation by hand, what you have to do is first find the expected value, which we did, 1.1. Then you take each of these values your random variable can take on, and you subtract the expected value. So you take 0 and you subtract 1.1. You take 1 and you subtract 1.1. You take 2 and you subtract 1.1. And we lost the 3. Did we have a 3? No, we just had a 2. And then you take each of those values and you square them. You multiply that by the probability, and then you add that up. So the standard deviation of this discrete probability distribution is 0.49. So much easier to do it on a calculator. Okay. See where we are here. Almost done. Okay, so you're playing a game of chance in which 4 cards are drawn from a standard deck of 52. You guess the suit of each card before it is drawn. So somebody has the deck of 52 cards, they shuffle them up, and before you ever draw a card out of the deck, you guess, is it a diamond, a heart, a spade, or a club? Which of the 4 suits is it? So then they put the card back in the deck and they reshuffle, and you pick another card. Now you pay $1 each time you play the game. So each time you make a guess, you pay $1. If your guess is right, so if you guess the correct suit, you get your money back and you get $256. What's your expected profit of playing the game over the long term? So no, this doesn't mean that when you play, you're going to win this much money, the expected value. You either win or you lose. One or the other. So you either lose $1 or you get $256. One or the other. You either win or lose. But over the long term, if you play the game repeatedly over and over and over again, the expected value is how much you could expect to, what's the word when you're betting? How much you would expect to gain or lose overall. That doesn't mean, that's one of the problems with gambling, is that if you do it once, if you do it over the long term, you're really not going to win money anyway, because you gotta hope for that one time when things go right, is what you gotta do. All right. So what do we got here? So X, our random variable, is the amount of money you profit. Because that's what we're interested in. How much money am I going to make in the long term? Okay, and what values can my random variable take on? Well, you can either lose $1, so you pay $1 and you lose, or you can win. So this is what it costs you to play. And this is what you could win. Okay, now what's the probability that you guess correctly? Okay, so you're drawing 4 cards out of the deck. So you draw a card out of the deck. Is it the suit that I guessed or not? You put it back in. You draw a second card out. So these are independent events, because what you draw out the second time doesn't depend on what you drew out the first time, because you put the card back. So when you draw a card from a deck with replacement, these make these events independent. So the probability that you guess the suit correctly Okay, so in a deck of cards, there are 4 suits, 13 cards each. So the probability that you guess the suit correctly would be 13 out of 52 for one card, or 1/4. So the probability that first card that you draw out that you guessed correctly would be 1/4. Now you're drawing 4. And since these are independent events and you're interested in, do I get it correct the first time, and I get it correct the second time, and I get it correct the third time, and I get it correct the fourth time, this is an and probability. And to calculate an and probability, you multiply the probabilities. So the probability you get all 4 cards guessed correctly is 1/4 times 1/4 times 1/4 times 1/4. So the first card is correct, the second card is correct, the third card is correct, and the fourth card is correct. So the probability of you guessing it correct is 0.0039. So the probability of you winning this game is less than 1%. That's why casinos stay open, because the probability of you winning is so small. In any game of chance, the probability of you winning is going to be very small. Okay, so now what have we got? So the probability of you not guessing correctly is 1 minus this, which is 0.9961. So how do you find the expected value? You take the value that your random variable can take on, and you multiply it times the probability that it takes on that value, and you add them together. So the probability of you losing a buck is 0.9961. The probability of you winning $256 is 0.0039. So if you add those together, so mu, I'm out of room down here, is the $256 times the probability that you guess correctly, minus a buck, times the probability that you guess incorrectly. And it's negative because you're losing money. So the 2 values your random variable can take on is -1, that you lose your dollar, or $256 if you guess correctly. So if you take your handy dandy calculator out and you multiply 256 times 0.0039, and you subtract from it 1 times 0.996, you get 23 cents. So over the long run, if you play this game over and over and over again, you can expect to win 23 cents. Now, again, that's not the way it works when you gamble. You either win or you lose. But if you keep playing, that's the problem. Once you win, you should quit. Editorial comment from Professor Castle. If you win, you should quit. Because if you keep playing, chances are you're going to start losing, right? It's just the law of averages. So when you start losing, this is what happened. So over the long term, if you keep playing, you could expect to win 23 cents. Woohoo! Big money. Okay, that's the end of the section. So I got 8 minutes. Let's real quick. Let's go over and remind you how to use your calculator. All right, here's my calculator. And I was doing an example for college algebra earlier. We were graphing. So let's get this off of here. Okay, so let's put one of those examples in. I don't know. Let's do the young lady Nancy attending class. So I'm going to go to my stat menu and see if I have anything on my lists. And I do. So I have something in L1, so I'm just going to go up and clear that out. Okay, so in L1, I'm going to put the values my random variable can take on. So she attended class no days a week, 1 day a week, 2 days a week, or 3 days a week. So I'm going to put in 0, 1, 2, really 2, honest, and 3. Okay, then what was the probability that she attended no days a week? Was that, where's Nancy at? That was 0.01. 0.01, Lisa. Okay. And 1 day a week was what, 0.04? 4% of the time she attended twice a week. 15% of the time she attended once a week, 4% of the time. Twice a week, 15% of the time. And then 80% of the time she attended all 3 days a week. Okay, so now I have the data in. I have the value that the discrete random variable can take on, and I have the probabilities of each of those random variables. So I'm going to get out of here. So I'm going to do a second quit. Then I'm going to go back in my stat menu, and I'm going to go over to calculate. And I'm going to calculate the one variable statistics. And my values of my discrete random variable were in my first list, so that's okay. But my frequency, the probability, is in the second list. So I need to tell my calculator that. So I'm going to go second, 2, and then I can calculate. So on average, she attends class 2.74 days a week. So over the whole semester, over the long term, on average, it's 2.74. Now, of course, that doesn't mean that she attends 2.74 days a week. Oh, I suppose she could leave class early. I don't know. But on average, that's how much she attends class every week. And then from this, you can see that it calculates the standard deviation for you. So you don't actually have to set up the table and do all these differences and squaring and summing up. It will calculate it for you. All right, are there any questions? You have an exam due Friday, don't you? On module 1, chapters 1 through 3, there is a review in your homework. There's a review for every exam. So you'll want to take a look at the review. Now remember the box plot thing that I need to give you credit for, whatever section that was in. There is the box plot question on the exam. Sorry about that. Because the rest of the problem's really good. It's just that drawing that stupid box plot. So again, if you get that correct, I will give you extra credit on your exam. So if your box plot gets credit, I will double the credit your box plot gives you. Whatever it gives you, like 0.3, point some, whatever it is, I will double that to 0.6. So if you get it correct, I'll give you extra credit. Whether it's on your homework, the quizzes, the review, or the exam, I will go in there and make sure you get credit for drawing that stupid box plot because it's so hard to draw. I mean, you have to draw the lines and it's too hard to draw. Are there any questions? Okay, well, if you've got your name typed into chat, I'll let you go and stay warm. Stay out of the snow. If it snows 20 inches, don't get in it. Be safe. We'll talk to you on Tuesday.
I have a question, but I'll wait.
I'm going to stop my recording.